So we're going to start spectroscopy. It's so exciting. Which is basically studying how light and matter interact. And so these types of measurements can usually be broken down into like some super simple components. So, and this is something that we do every day. So basically you have a source, you have a sample, and you have a detector. And sometimes there's wavelength differentiation as well. So basically if you have sun, it shines off a red t-shirt into your eyeball. You have a source, which is the sun, the sample, which is the red t-shirt, and your eyeball, which is the detector and wavelength differentiator, because we're seeing different colors. So that's sort of the premise, and we're going to explore that in much more detail. Alright, so first we need to know something about light. So, right off, light is, I use light and the term electromagnetic radiation interchangeably. So light to me could be anything from X-rays all the way down to microwaves. And that's just sort of how I think about it. So just going to give you that bias up front. So basically, light can be described using a frequency and a wavelength. So the frequency is measured in hertz or cycles per second. Wavelength is measured in meters and can be and these two, frequency and wavelength, can be related through c, which is the speed of light. So it's basically 3 times 10 to the 8th meters per second. You can also say that a photon has an energy. And so you can calculate the energy of that photon using the frequency and the Planck's constant. So energy equals Planck's constant times frequency, or times h times 1 over h over lambda. You can also talk about wave number, which is 1 over lambda, and that's used a lot in like infrared spectroscopy when you're talking about long wavelengths. So that's a term that you're also going to be seeing at some point in this discussion. Alright, so let's talk briefly about the electromagnetic spectrum, and I'm going to show you a better picture in class, but basically you have radio waves, microwaves, infrared, visible, UV, X-rays, and gamma rays, and those are listed in terms of increasing energy. So basically we can talk about the different, since this is increasing energy, we can talk about different molecular transitions or whatnot that you can excite with increasing energy. So we'd start with rotation, molecular rotation, and that's pretty easy. That's low energy, so that's why microwave works to warm up your food, because it's getting a lot of rotation out of the water molecules in your food, and that's what makes it warm. You can excite vibrations using infrared spectroscopy or infrared light. We can look at electronic transitions within molecules using visible or UV, ultraviolet light. X-rays are used for maybe bond breaking or ionization, where you actually eject a core electron from the atom. And gamma rays are involved with nuclear transitions. So you have increasing lambda, increasing wavelength as you go up, and decreasing, let's see, so decreasing frequency. Alright, so basically what happens is that you have light coming in, it hits a molecule, this is for UV visible, but the sort of the idea is translatable. So you have light coming in, you have an electron that's excited into an excited state, and then you can have relaxation back to the ground state. And we're going to get to more of that probably next time. So, alright, so basically we have a source. We're going to put the monochromator in front of the sample at this time. So we're going to have a single wavelength going into the sample. So we have the incoming beam as a P0 or P0, and then after it's going to interact with the sample with a wavelength of B, and then after it comes out, it's going to have a power of P, and then it's going to go to the detector. So we can think about how we can describe the interaction of this beam with the sample in a couple of ways. We can think about the percentage that's transmitted, or the amount of light that's transmitted through the sample. So basically P divided by P0. Or we can talk about the absorbance, which is basically the log of P0 over P, which is negative log of T. And the reason we like to think about absorbance is because Beer's law basically shows that the absorbance at a specific wavelength, lambda, is equal to, related to the concentration by basically A, so the absorbance at a given wavelength equals the molar absorptivity at that same wavelength for your analyte species times the path length times the concentration. And these are wavelength specific. And basically, molar absorptivity has the units of moles per liter. Let's see. The units of molar absorptivity are molarity, 1 over molarity times 1 over centimeters. So it's molarity to the -1 times 10 centimeters to the -1. Path length is measured usually in centimeters, and it's usually pretty close to 1 centimeter. And then C is the concentration in usually in moles per liter. Alright, so let's, so the chromophore is basically the molecule that absorbs light. And so Roy G. Biv is basically the colors of the rainbow. And so I put up the energy of the different lights in nanometers around the circle. So the point that I would like to make is that actually the color that you see is not actually the color that's being absorbed. So in order to find the color of the red t-shirt, you're going to have to go directly across the color wheel, and actually the shirt is red because it's absorbing green light. Alright, so that's all you need to know for to introduce you to spectroscopy. We're going to get into a bunch more details in the coming sessions.